Welcome to Pavnars, webinars for the pavement community. My name is Andrew Braham, and today we're going to talk a little bit about developing a particle size specification for asphalt emulsion. This is based on Mr. Logan Kiihnl's Masters of Science research here at the University of Arkansas. Logan obtained his Bachelor's of Science in Civil Engineering in 2018, his Master's of Science in 2020, and you can see more in his LinkedIn profile, which is also posted below. Let's start out by defining an asphalt emulsion. And before we define an asphalt emulsion, let's just define an emulsion. An emulsion is two liquids, which can be liquid 1 and liquid 2, that cannot be mixed or dissolved. Liquid 1 is suspended in liquid 2. Liquid 1 has some sort of chemical on its surface, and the chemical prevents liquid 1 particles from joining together. So this is a general definition of any emulsion. Now for an asphalt emulsion, we can substitute materials in for these liquids. So for an asphalt emulsion, you have small particles of asphalt binder that are suspended in water. The asphalt binder can't be dissolved or mixed into the water, and the asphalt binder is suspended in the water with the help of emulsifiers. So if you take a look at the image on the right, you can see the circular asphalt binder droplets, and then you have some asphalt emulsifiers that suspend those asphalt binder droplets in the water. Now there are a couple of asphalt emulsion standards that are important, and I'd recommend you get your hands on these if you have the opportunity. For material specifications, you have AASHTO M140, which is for emulsified asphalt, M208, which is specifically for cationic emulsified asphalt, and M316, which is for polymer modified emulsified asphalt. There are various testing standards as well. T59 is the main one. This is emulsified asphalt, and it revolves around the testing of emulsified asphalt. Also of particular interest to this presentation, we have AASHTO T382, which is viscosity by a rotational paddle viscometer, which you can see on the right. And there's also a standard practice, AASHTO R5, which is selection and use. And this links different emulsions to various treatments that you can use those emulsions in the field. Now let's specifically dig deeper into AASHTO T59. AASHTO T59 can be divided into 4 general sections. You have the composition section. In the composition section, it tells you how to measure the water content, the residue and oil distillate by distillation. It has a residue by evaporation, and it has a particle charge in T59. In the consistency section, they have viscosity, specifically Sabalt viscosity. In the stability, they have demulsibility, settlement, cement mixing, sieve, coating, and storage stability. And then in the residue, they have specific gravity, ash content, solubility, penetration, ductility, and the float test. So these are the 4 main different categories, and these are the various tests that fall underneath each one of those categories within AASHTO T59. And what we can do is we can map these tests to M140, M208, and M316. So if you take a look at those 3 specifications, they have some sort of combination of the tests below. So for emulsified asphalt, M140, M208, and M316 have some sort of combination of viscosity, whether it be Sabalt or paddle, storage stability, demulsibility, sieve, cement mixing, oil distillate, and distillation to obtain residue. Now for the test on the residue from distillation, M140, M208, and M316 have some sort of variation of penetration, ductility, elastic recovery, softening point, ash content, and float test. So if you go to M140, M208, and M316, and you look at all the different asphalt emulsion grades that are listed in those standards, you will see the requirements for each one of these tests, and the majority of these tests can be found in AASHTO T59. Now, I'd like to go back in time a little bit. if we take a look at a paper that was published in the Association of Asphalt Paving Technologists, or AAPT, Volume 9, back in 1937, the paper is titled The Testing of Bitumen Emulsions. And this paper looked at these different properties: the water content, dispersion, storage stability, both short and long term, coagulation at low temperatures, viscosity, and rate of break. And if you look in Britain in 1937, that was where the author of this paper was from, they have various tests that measure these properties. So you can heat the emulsion with xylene in a sand bath. You can pass the emulsion through a number 100 sieve. You can let it sit for 7 days and pass it through a sieve. You can let it sit for 3 months and pass it through a sieve, and so on and so forth. But you can see all these different types of tests that are run in 1937. Now, if you take a look at AASHTO T59, you can directly link several of those tests to tests that were developed in the 1937s or before. That means that a lot of the tests that we're using for asphalt emulsions and quantifying their characteristics are 80, 90 years old. That's absolutely insane. So there are tests that have been developed since 1937. And one that is of particular interest is particle size. Because if you go to conferences that talk about asphalt emulsions, they talk a lot about particle size. And just one example is the Transportation Research Circular EC 102. It's called Asphalt Emulsion Technology. It was put out in August 2006, which is a while ago, but there's still a lot of good information in there, and it's free. These TRC circulars are absolutely fantastic. I'm a huge fan. Lots of good information in these, including EC 102. Now, there's 2 quotes in particular that I'd like to highlight from this circular. You can see here, particle size strongly influences the physical properties and performance. And you can see here is an example of a particle size distribution from EC 102. You got your volume on the y-axis, you have your particle diameter. You'll note that's in microns on the x-axis. And this just happens to be different residues, same emulsifier, but different residues and the particle sizes associated with those residues. But the point is that the author of this felt that the particle size and the distribution influences not only the physical properties, but also the performance. And later on, you can see here that they talk about adjusting the particle size can control physical and performance properties. So this is just one example, but if you go back through literature, if you go back through conferences, people talk a lot about particle size and they talk about the importance of particle size. However, there is no standard for particle size of asphalt emulsions. And so what Logan did is he took the first step. He took 8 emulsions and he actually purposely made these outside of the recommended ranges. So he had a proprietary cationic slow set emulsion and a commodity cationic medium set emulsion, and he did various combinations of a high and low emulsifier dosage, anywhere from 0.15 to 1.75% of emulsifier. He put no acid in. He put a high level of acid in, well, a high pH using acid, which is 5.0, and a low pH at 1.0. And these are high and low in relative toward cationic pHs. And he used a recirculating Herbert Rank mill at 15 seconds of recirculation and 45 seconds of recirculation. So these were the 8 emulsions that he made outside of the recommended range. And he also compared it to in-range emulsions. So we base this concept of ranges off of information sheets from a emulsifier supplier. And the ranges, we also picked right in the middle of all of the ranges. So a CSS at 1.15% emulsifier with 4.5 pH and 30 seconds of recirculating mill time, and the commodity CMS at 0.3% emulsifier, 2.75 pH and 30 seconds. So we had some emulsifiers that were kind of right at the range, the edge of the ranges, just outside of the edge of the ranges of the recommendations, and then ones right down the middle. And then we tested these emulsions that we made at 2 hours, 1 day, 4 days, and 7 days using a Beckman-Coulter multi-sizer for using the paddle viscosity. And just to reiterate, CSS is cationic slow set, CMS is cationic medium set. And to clarify, we tested the particle size at 2 hours, 1 day, 4 days, and 7 days, and we measured the viscosity at those 4 time periods. Now, the first thing that we kind of took a look at was this concept of the smoothness of this distribution. And one of the reasons that we did this research was there's a lot of features on particle size analyzers that you can change. For example, one of them is the sample volume and how many numbers of particles you count. And because there's no standard, we don't have any guidance on if there is an acceptable number of particles counted or an acceptable amount of volume. And so you can see here, this is the same emulsion, but we're just counting different numbers of particles. And so you can see the volume on the y-axis again and the diameter on the x-axis. And you can see when we're counting low number of particles and a relatively low sample volume, you get a very strange kind of mountainous graph with a lot more particles shifted to the right, so higher particle diameters. But using the exact same emulsion, increase in the number counted, increase in the volume, it smooths the graph and it shifts it a little bit to the left. So as the number count increases, the graph smooths. That's number one, and that was very consistent. And for this particular graph, it also shifts it to the left, so the particles become smaller. And it's the same material with no guidance on how many particles to count, what kind of volume to be looking at. We could have recorded both of these and felt we were not going amiss. Now that we knew a little bit about the number of particles to count and the volume of particles to count, the first thing we looked at was viscosity versus the time versus manufacture. And you can see there's a little bit of nomenclature going on here. All of these are CSS, cationic slow set emulsions. But you can see you have a D, you have a P, and you have an M. The D is the emulsifier dosage, the P is the pH, and the M is the mill time. And these were at a high and a low volume. So the high value was just outside the emulsifier range. The low value was just outside the emulsifier range, and corresponding pHs and mill times. So this is a partial factorial experiment, but we've got viscosity versus the time versus manufacture, and we have different levels of emulsifier dosage, pH, and mill time. Now, the biggest takeaway from here and the clearest takeaway was that the viscosity increased as the storage time increased. Now, taking a look at the same concept, but using particle size instead of viscosity, again, looking at the same emulsions, here we can actually see that the mean particle size did not change over time. And this is very unexpected. If you look at literature, if you follow what people talk about, in general, people feel that the particle size increases over time of storage because the particles start falling out of suspension, they start coagulating, they start flocculating, they start joining together. So this is a little unexpected, but it is what it is. It is what was recorded. And so what we did with all of our emulsions is we tried to correlate the viscosity to the particle size. So you can see we got the mean, the D10, the D50, and the D90. We have a passing viscosity and we have a failing viscosity, and we measure the corresponding particle size at the passing and failing viscosity. Now let's go over a little housekeeping. D10, that means that 10% of the volume of the particles were contained within the particle size distribution. So 10% were smaller, 90% were larger. D50 was 50% of the volume was contained. That means 50% was smaller, 50% was larger in that particle size. And then D90 is 90%. 90% was smaller, 10% was larger. That's D10, D50, D90. So this is the data for the particle size with CSS emulsion. We also have the data for the particle size of the CMS emulsion. And again, what we did is we looked at the passing and the failing viscosity. What we tried to do was, if we knew from AASHTO standards which emulsions would fail with viscosity, could we correlate those failing viscosities to failing particle size? If we knew which emulsions passed the viscosity, could we correlate the passing viscosity with particle size? And this is what we came up with. So for CSS, we thought that 2.2 microns was the D10, the minimum D10, 2.6 for CMS for the D10, and then the corresponding mean of D10. So that was the average value of D10. So we had not only a minimum value of D10, but a mean of D10. Then we had a minimum value of D50 and a mean of D50. So minimum for D10 of 2.2 and 2.6, mean D10 of 2.4 and 3.2, and then greater than D50 of 4 and 5 for CSS and CMS respectively, and then a mean of 4.4 and 6.9. So in conclusion, only 10 emulsions were manufactured. This is a relatively small data set, but as I mentioned, this is the first step. 5 were CSS, 5 were CMS, 8 were just outside of the recommended ranges for emulsifier loading, pH, and recirculating time, and 2 were in the middle, in the sweet spot. And what we did is we created 3 samples and we ran each sample 3 times. That gave us 9 curves. So as a sample circulates or goes through the equipment, it captured 3 different distributions, 3 sets of distributions. So we had 9 different curves. We recommend a minimum number count of 5,000 particles and a minimum total particle volume of 70,000, excuse me. This is what we believe gave us the most representative and consistent particle size distributions. And we also have those 2 in the middle of the recommended ranges that really helped us hone in on what were the appropriate number of runs, the minimum number count, and the minimum total particle volume. And again, our preliminary recommendations was for CSS emulsion, you wanted a mean D10 of 2.4 and a mean D50 of 4.4. And for CMS, a mean D10 of 3.2 and a mean D50 of 6.9. So the first step, truly more work needs to be done with this. More emulsifiers need to be looked at, more binders need to be looked at, they need to be correlated to performance tests, but this is the first step, trying to understand, can we quantify what acceptable particle size is, and can we start the conversation of developing a specification? So I just covered the highlights. If you're interested in learning more, here is the full citation. Here is a link to the DOI number, and that link can also be found in the discussion section below. But I appreciate you joining me today, and I hope you have a wonderful day.